Hi, I'm Minglu from Shenzhen University. I'm very happy to present our work here on exploring visual information flows in infographics. This is a joint work with researchers from China, US, and Israel, Chufeng, Zhao, Cherry, Hanspeter, Danny, and Huang. My work is about infographics. Infographics are very eye-catching visual designs. I'm very interested in infographics, not only because they are very visual appealing, but also they always tell stories. By a blend of graphical elements and data in structured way, infographics can convey the information to readers in a nice way. In well-designed infographics, we always know how to trace the data elements and get the story. For example, in these infographics, I believe most of us go through those elements in this way. And the flow that leads us to get the story is visual information flow. And in this work, we focus on analyzing this kind of flow. Although information can be very differently designed, but some of them do have very similar flows. For example, in these two, the information goes in a zigzag flow, and in these two, the information goes from up and down and from left to right. So in this work, we want to explore and learn the design patterns of visual information flow in infographics so that we can have a better understanding of infographics design and more generally, visual organization of storytelling. But this is a very challenging problem because designers may use various creative means to design infographics, which make the analysis of their design style super hard. For example, the visual elements can be designed with various appearance, even injected with the designer's personality and style. And also, the spatial arrangement of those elements can be very unique and only crafted for certain storytelling purpose. So, to do this, we collect a large amount of infographics from two designer websites, FreePic and Shutterstock. The infographics collected from those two websites are contributed by designers all over the world, and those infographics are more like design templates. For the example I show here, in these templates, elements are always well designed. For example, icons are consistently designed and texts are with similar font size and style. And on the other hand, those infographics are very diverse in their design, which provide a good coverage of the design space of infographics. Now let's see how we deal with such a large number of infographics and learn its style. Let's consider an infographics here. Designers always create infographic by composing multiple layers. And they may have a layer to deliver certain information, another layer to create visual effects such as shading. But basically, an infographics can be decomposed into two layers. A layer of artistical decorations, which will make the infographics visually appealing, and the other layer of data elements, where the information flows. So, our work consists of two parts. The first part is to peel off those artistical decorations and get the data elements. And then we construct visual information flows from those data elements. So in the first part, our input is the original infographics. We leverage the power of neural network. Specifically, we adopt YOLO, an advanced objection detected model, and train it from scratch with our own data set and make it able to detect the data elements. And in the output, each element is categorized by a tag and as well as its boundary box to show where it is. To train a successful network, the key is to feed it with the right training dataset. In our case, we developed a very simple interface to manually label the infographics. We categorize data elements by 7 groups, such as icons, texts. For those groups, we further distinguish it by subcategories. For example, numbers, we have 10 subcategories from 0 to 10. Using this interface, we manually labeled 4,000 infographics. And then we apply image augmentation methods, generate gray version of the infographic, so we double the size of the training dataset. We also crop subregions to get more dataset. In the end, we get 23,000 images. And with this training dataset, we are able to make the neural network work. So here are more examples. The average detection precision is around 63%. It's not very high precision, but it's reasonably good. There do have some misdetected elements, and I will introduce you how we deal with those missed elements in the construction part. But now let's look at the detection result on the left. When we see this, we can actually have a very good guess of the flow. It probably goes like this. And yes, this is the original infographics. So what supposes us to have a good guess? Let's elaborate this problem with one more example here. Is there anything strange? Yes, we may notice there is something missing here. Actually, when we read these infographics, we do some mental work unconsciously. We compose visual elements which depict the same piece of information into groups. Like here, icons, texts, and the number of years are composed as visual groups. And we can easily get those visual groups because designers has already adopted some design principles, that is the Gestalt principles, in their design. For example, they use the proximity principle to make elements in a group close to each other, so we won't detect this icon is with the same group as those texts. And second principle is similarity principle, that groups are always configured with similar configurations. Here, each group has an icon, text, and a number, and that's why we see there is something strange when the text is missing in this group. And another is regularity principle, that is, groups are always placed in a harmonious patterns. For example, designers would avoid long jump as much as possible to make users easily track those groups. So with those principles, the basic idea in VIF construction is we first take those detected elements as input, then we construct the backbone, and then we associate those elements in a group. We develop a rule-based algorithm. The key idea is to score all possible tracing of those elements, we choose the best one. Here shows some examples. As I mentioned before, because our neural network cannot detect all the data elements, so in some cases, those elements can be misdetected. So in our algorithm, we can infer those elements by the similarity of groups. So we can recover them, some of them. Here shows more example. The gray dashed rectangles are those elements inferred. Now we get the visual information flow by a backbone and a group associating links. So to explore the design space, we transform the visual information flow to a visual information signature The signature is a image page 100 by 100 size. And in this image, we draw those backbones with thicker strokes, and then we draw those group links with thinner strokes to make it a secondary feature. So by this transformation, each infographics is transformed to a 10,000 high dimension data. Then we apply the Disney projection to see it in 2D space. On the right, I shows a close-up of the region highlighted in left, and we can see on the top part, the VIF are more W shape, and here are more spiral, and here are more like a vertical line. So in this space, we perform the semi-automatic clustering to get the VIF patterns. And we get 6 main patterns as shown here, including landscape, portrait, clock, etc. And also another 6 that's notable patterns. This is the dynamic navigation in this projection. Taking VIF as a high-level feature of infographics, it also supports us to query those infographics. We develop a prototype to show this idea. To draw the conclusion in this work, we explore visual information flow in a large amount of infographics, using deep neural network to detect the data elements and construct visual information flow based on Gestalt rules. And in the end, we distill 12 main visual design patterns. And also we discussed the taxonomy with 2 dimensions, but I didn't introduce this in my talk. If you are interested, you can look into our paper for more details. And we also developed an infographic searching engine, which we can take the flows as high-level features. And we also release our dataset to the public. And if you are interested, you can go to this link. So thank you very much. Thank you for your attention.